this coming time in, I think it's April 8th, the moon will be right about here for us, and Mars will be right about there. So it'll be a very nice view for binoculars. So that's kind of why I thought of the whole thing, to bring them along. So that's all I have.
Dewey, and I just want to say a few words about his background. Come over here in this direction. So Dewey has degrees in math, physics, computer science, and a master's degree in astrophysics. That one's from the University of Colorado at Boulder. He's got classes to undergraduates there at CU, right, and other places too. And as well as he has a computer graphics programming degree from the University of Florida. He's been an active member of the Mars Society, and that's where how many got the MailChimp email I sent out? Did everybody get that? The email I sent out a few days ago? We're now in the modern age, and instead of me sending your email in 5 groups, because I'm afraid of spamming, we now have MailChimp, which allows us to do it all a lot quicker. And thank you, John. You set this up for us. So if you got this, you probably saw this picture. And Dewey with the Mars Society, how many years ago was that?
2001.
2001. He actually designed and created these suits for the Mars Society. Does something. They've got 2 stations where they do simulated missions. You can go there. You could go if you wanted to. You could apply for about 7 days with a crew, and you live with them in a very small unit. That one's in Utah in the desert, the other one's in the Arctic Circle. They're still using them, right? Are they?
Yeah, not as much.
But just in the summer, yeah. And they got polar bears that come in too. So, yeah, and Mars Society, Robert Zuberman runs that, will probably give us a talk this summer too. He lives down in Denver. So, I don't know if you have a picture of that, Dewey, but he and another Mars Society person actually tested out these suits, took some pictures around Barker Reservoir. Do you have that in there?
No.
No, okay. But, yeah, so it's got a real local angle, too.
I could bring it up for you if you really want.
Yeah, okay. And Dewey has agreed, even though this is kind of a long talk, but he needed that much time. We're very hard to get this down. And he said you can ask questions. If you ask something that needs more of an explanation, he may go to the last. But I badgered him for months. He finally agreed, to let people ask questions too. And I'll turn it over to you.
All right. Going to get the control here so that I know what I'm doing here.
And you
Yep.
Okay.
Okay.
Good.
So, this talk was motivated by a question somebody at a previous meeting posed. They said, wait, doesn't it take about 3 years to get to Mars? And no, it doesn't take 3 years to get to Mars. But I thought, rather than just say how long it takes to get to Mars, I could just go through and show you how you can calculate how long it gets to Mars. So that's kind of what this is about. So that means it's a little unusual compared to most of the talks we have around here, because it's about physics. Orbits come from gravity, gravity comes from physics. So this will be kind of a physics talk. If you saw my talk on spectroscopy about 1.5 years ago, I showed a bunch of equations in that. And some of them were pretty messy, but I didn't say, oh, let's now do a calculation with this equation. I just wanted you to see the equation, point out, so, well, here's where the temperature's involved and that sort of thing, so you could see that they existed. In this talk, I'm going to give you equations, and we are going to do calculations with them. But they're much simpler equations. So, if you can do multiplication and division on a calculator and take a square and a square root, you'll be good. It takes scientists to come up with these equations. It doesn't take a scientist to use them. And that's kind of my point. I want you to come away from this going, hey, I could do that. If I want to figure out how long it's going to take to go from Mars to Neptune on the most economical path. Well, you ought to be able to figure that out. And so, in conjunction with that, I'm given a handout here. I have to pass that around. And this side. And basically what it has is these equations, so you don't have to try to remember them. And then a bunch of data about the solar system, planetary orbits and masses and stuff, just so you don't have to go look them up on Google like I did. But that's where the stuff comes from. It comes from Google. So, but if doing arithmetic bugs you, don't worry about it. You can just skip while we do arithmetic and just look at the final answer and see how that was done. And now, before I get into that, I need to admit something. I am not an expert on orbital mechanics. But again, it's kind of my point. If I don't have to be an expert to show this stuff to you, you sure don't need to be an expert to use these equations and play around with. Okay, so here's the plan for the talk. I'm going to start with a little anecdote, motivation stuff, and then some background stuff explaining just what we mean by a force, and then I'll talk about gravity. And one of the things I want to talk about in gravity is what weight is and what weightlessness is, and what weightlessness isn't. It's not just being up in space. And then after we do that, then I'll talk about orbits, and then we can get into Kepler's laws of planetary motion, and that's the sort of thing that allows you to calculate how long it takes to get to Mars. So, let's get motivated here. June 1965, NASA launched the Gemini 4 mission. This was the second manned mission with the Gemini 2-person spacecraft. And at this point in the space program, we had half a dozen Mercury missions. And, first two were suborbital, then we had 3 orbits, 6 orbits, and 22 orbits. Last Mercury mission, the guy was in space for 34 hours, which is pretty long. And then the next was the Gemini missions. And this is to test out the technologies they knew they were going to need for the Apollo program. It had 2 seats, as you can see. And one of the techniques they were going to do is rendezvous and docking. So, in the Apollo program, the command service module is going to have to dock with the lunar module twice. Once on the way to the moon, and then again to come back. So they had to work these techniques out in the Gemini program. So here's the Gemini list up to this point. First 2 were unmanned missions, and then they had Gemini 3 was just the first test drive. This is, okay, now you got people in charge. They only went to 3 orbits, said, it's go, you can use it. And then this is the one we're going to be interested in. And then after that, there were a whole bunch of missions that tested out rendezvous and docking, long-duration spaceflight, worked on their space walk techniques. And what Gemini 4 is most known for is that it had our first spacewalk. Now this is a big deal for the US because the Russians had already done a spacewalk, so we were behind in the great space race. But the other thing they knew they're going to need to do with this rendezvous and docking. And in future missions, they were going to dock with this Agena satellite. And so it's moving around in space, plug in, and connect to it. That's their practice for what Apollo's going to need. But before they were going to actually do those in the later Gemini missions, in the Gemini 4 mission, they wanted to just practice a little rendezvousing. So what they figured they would do is, this is the top stage of the Titan booster that put them into orbit. They're just going to fly up close to the thing. No docking, nothing fancy like that. Just to show that, yeah, we can fly along with something going 17,000 miles an hour in orbit. So they separate from the booster, turned around, and astronaut James McDivitt tried to do that. And Gene Kranz, in his book, Failure is Not an Option, described that this way. You all open your hymnals now to feeling preaching up here. Okay, 5.5 minutes after liftoff, McDivitt reported booster cutoff. He waited until the booster thrust had decayed, and 20 seconds later fired capsule separation pyrotechnics and then maneuvered away from the booster with the Gemini thrusters. After he turned around, he saw the booster about the length of a football field away. McDivitt braked the Gemini and briefly fired thrusters to close the gap. Minutes later, perplexed, he reported the booster was now moving away and down from the Gemini capsule. In Mission Control, Llewellyn, one of the guys in Mission Control, stood up at the retro console and started talking over the intercom to Kraft, who was the flight director for this, gesturing with his hands like a cab driver in Rome. He was trying to explain what was causing the problems for McDivitt. As the reports came in with night rapidly descending, McDivitt again thrust toward the slowly tumbling booster. The range increased to 2,000 feet, then appeared to decrease, and then increase again during the night. Coming into daylight, the booster was now over 3 miles away. McDivitt checked his fuel quantity, conferred with Kraft, and observing the cutoff limits, terminated the attempt to rendezvous with the booster. As I sat in Mission Control Center, I was baffled by the problems. Unwittingly, Jim had kicked open the door to the mysteries of orbital mechanics, and I had a new respect for Lundy and Llewellyn, who quickly mastered the mysteries of trajectory control. After the mission, we reconstructed McDivitt's maneuvers. Following separation, he was ahead of the booster in orbit, and as he thrust toward the booster, he was performing a slowing down maneuver. As the spacecraft slowed down, it went into a lower orbit. To balance the force of gravity, a spacecraft in a lower orbit, no matter how slightly lower, must travel faster than one in a higher orbit. Thus, by slowing down, McDivitt was descending and going faster, pulling away from the booster's orbit. In the trajectory world, you have to reset your mental gyroscope. Orbital mechanics are counterintuitive, particularly for someone used to flying an aircraft which follows an entirely different set of rules. I realized then that orbital mechanics was something else I needed to learn a lot more about, particularly if I wanted to be ready for the far more complex orbital maneuvers involved in a rendezvous. So tonight, I'm going to explain things so that you'll know how they got it wrong. Okay, so like I say, I'm going to be doing a bunch of equations. Before I get into the equations and numbers, I want to say something about the units I'm going to be using. I'm going to be using metric units. That's what scientists use. This is science, so let's use science units. And every so once in a while, I'll convert them over to something you're more familiar with, like miles an hour or something. But you're actually, the metric units and English units aren't that radically different. If you just think a meter, oh, it means about a yard. Kilometers, about a mile. Kilogram, and it's up on the order of a pound of mass. And then a newton of force, which we'll see, and that's also about a pound of force. Well, maybe a quarter pounder instead. Okay, and speaking of these calculations, you're going to see a variety of numbers of digits of precision in these things. When you're doing these things on a calculator, or as I did in a Python program, it's very easy to carry along a zillion digits of precision. So you might see that, but I'm not going to put those big long numbers up on the slides, and I'm certainly not going to bother saying 1.2, 3, 4, 5, 6, 7, 8. So I might say, about 1.2. So I just want to give you a heads up. If what you hear me saying doesn't match what you see, and doesn't match what the calculation would be, that's all that's going on there. Okay. Force and acceleration. Before I talk about orbits, I need to talk about gravity. Gravity is a force. So I need to say something about force. Force causes acceleration. Okay, so now I need to say something about acceleration. Acceleration is the time rate of change of velocity. We all know what velocity is. That's the rate of change of your position. So if you're going 30 miles an hour, we all know your position changes by 30 miles in 1 hour of driving. We know you don't have to drive for an hour to be going 30 miles an hour. That could just be 15 miles in half an hour, or a mile in 2 minutes, or half a mile in a minute, or as it happens, 44 feet in 1 second. So, flipping the page here. 30 miles an hour is the same as 44 feet per second. We write that algebraically like this. And so, per hour or per second means divide by. So, let's say you're initially going 44 feet per second, and then 2 seconds later, you're going 50 feet per second. So, what was your acceleration? It's your change in velocity divided by your change in time. Well, there's your 50 minus 44, that's 6. That was the change in time with the 2 seconds. 6 over 2, that's 3. You don't need your calculator for that. And you have 3 feet per second. And so they simplified this by saying, look, if I am dividing by seconds on the top and then dividing that by seconds again, that's really by dividing seconds times seconds, so it's seconds squared down below. I'm just going over this simply because you're familiar with miles per hour. You talk in terms of velocity units all the time. You rarely talk in terms of acceleration units. And that's our acceleration units, is feet per second squared. Wait, I said I was going to do metric units, didn't I? Okay, so you travel in meters, and then your meters per second, and then it's meters per second squared. So, if you know the acceleration, then you can compute the motion. So, if your acceleration is constant, there's a nice simple little equation here. And what that says is, how far will I go, y, if I have a constant acceleration a, and I do that for t seconds. So I just need to plug in the numbers in there and crank out the numbers. I'll see how far I go. So let's say I am accelerating at 4 meters per second squared. I'm going to do that for 5 seconds. I plug those numbers into this equation. So there's my a is 4, my t is 5 squared. Well, let's see, a half times 4, that's 2. 5 squared is 25. You've gone 50 meters. So starting from a stop, if you accelerate at that rate, in 5 seconds, that's how far you go. Now, this is what I mean when I say we're going to be doing calculations. Okay? This equation with numbers, with letters. I tell you what values the letters have. You plug them in. I won't bother with all these intermediate steps, but then we'll just hop down and see what the answer is. So that's what I mean when I say we're going to be doing calculations. Now, as it happens, a car, if that's what we were talking about with acceleration, probably not accelerating at a constant rate. So this equation doesn't really quite hold for that. But we're going to see later that there are some situations where you can use the acceleration of gravity and it will be constant enough that we can use this formula. Okay. So, hey, I'm ready for a definition of force. Newton expressed force here with his 3 laws of motion, which really kind of boil down to one, which is F equals ma. So, in this case, F is the force that we're talking about applying, little m is the mass of the object, and then a is the acceleration of that object due to a force. That's what a force is, something that causes an acceleration. Now, I'm going to give you a little heads up. Sometimes you'll see little m, and it means the mass of something. Sometimes you'll see a little m, and it means meters, as in meters per second squared. So it's not as confusing as it sounds like it might be, but I just wanted to give you a heads up on that. Okay. So let's do an example. Let's say we have a mass of 3 kilograms. We want to accelerate it at 2 meters per second squared. We've got F equals ma. We plug in 3 kilograms. Oh, look, that means mass. That means meters per second squared. Okay? We get 6 kilograms meters per second squared. That's kind of a messy thing to have to say. So they came up with a new unit called the Newton. So that is, that set of units right there is called a Newton of force. So that's our metric unit for force. Hey, I'm almost at the end of that. So a Newton, I showed you earlier, is about a quarter pound of force. So you can convert from one to the other if you have to. Okay? That, a little background stuff I wanted to cover for people who haven't seen this sort of thing in a long time, or ever. Okay, now E is the stuff that makes you stick to the Earth. It makes fly balls come down in the outfield, and it keeps the planets from zooming off into space. Classically, it's described with this equation, also from our friend Newton. F equals big G times big M times little m all over R squared. So that's the force. Big M is the mass of one of the two objects, usually taken to be the larger of the two. Little m is the mass of the smaller object, or one of the objects, usually taken to be the smaller. So it might be the mass of the Earth, it might be the mass of a person, using that equation. I should point out that it's proportional First off, it also works if both masses are the same. Like you got a binary star system, the two masses are equal. But normally what we're going to be talking about is what's the gravitational force on a little thing, like a satellite or me, due to the big thing, like the planet Earth. Or maybe the little thing's the planet Earth, but the big thing is the sun. It's proportional to the two masses. So what I'm saying there is, if I double the big mass of the planet's twice as big, I can factor that 2 out, and I've gotten twice the original force. Same thing with a little m. If I double that, maybe 2 people are standing on the scale instead of just 1 guy. I can factor that 2 out, the force has doubled. So it is proportional to the two masses. R is the radial distance between the two. You could use D for distance if you wanted to, but R is the normal thing used for this because we're talking about radially straight out from one object to the other. What's that distance? Okay, so notice it's down the denominator squared. If you saw my spectroscopy talk, you might recognize this as an inverse square relationship that I talked about. If I double R down here where it's squared, pull that out, 2 squared is 4. Doubling the distance divided the force by 4. That's an inverse square relation. Okay, so we've got that it is proportional to the new masses, inversely proportional to the square of the distance. Capital G, that's Newton's gravitational constant. In its sense, it's kind of converting from kilogram, or meters squared into units of force. And it has the value 6.679 10 minus 11 Newton meters squared per kilogram squared. Now, if you haven't seen scientific notation in a while, I will remind you that times 10 to the minus 11 means I take this number and I divide it by 1 followed by 11 zeros. So it's a pretty small number. And G, the nice thing about it, it's a universal constant. That means it is the same for every problem you might want to do. So if I'm doing me and the Earth, big G has this value. If I'm doing the Jupiter and the Sun, the forces, G has this value. So it's not something you have to look up for every single problem that you're doing. So let's do an example. Me, standing on the ground. There's our formula, big M, little m, r squared. Okay, what's the mass of the Earth? I looked that up, 5.974 times 10 to the 24. Scientific notation again. If I'm times 10 to the positive 24, now I'm saying multiply by 1 followed by 24 zeros. That's a pretty big number. Me, I'm about 87 kilograms. And so what do? Oh, radius of the Earth, 6,378 kilometers. But that's kilometers. We want meters, so I multiply that by 1,000. There's my radius of the Earth in meters, so we're all in the same unit system. Plug those numbers into that equation. So there's big G, there's big M, there's little m, there's r squared down at the bottom. You get out your calculators, you multiply that all out, boom, that's what you get. Multiply these 3 numbers, divide by this, you get about 853 newtons. That's my weight. The force the Earth is pulling on me. If I want to see that in English units, you probably you don't know what to think of when I say, oh, my weight's 152 newtons, 153 newtons. Multiply that, about a quarter pound per newton, get 190 pounds roughly. So that's my weight.
You should say that's pound force, not pounds weight, because it's a big difference.
Oh, actually, pound weight and pound force are the same. Pound mass is different.
Yeah.
And I considered following that alley and decided I didn't have time for it. But yeah, that's pounds of force. And that's my weight. Okay. So what is this distance r? You may have noticed back here, for r, I used the radius of the Earth. And you might look at that and go, well, no, wait a minute. If you're standing on the Earth, isn't that distance 0? But it turns out for calculations like this, no, you don't use that. You actually use the radius of the Earth. And here's the quick and dirty reason why. It comes from two things. An assumption we're going to make that simplifies things, and then some calculus, which we won't be doing here. The assumption is that the Earth is spherically symmetrical, density-wise. So what that means, you can imagine it's a bunch of different shells. Every shell has a uniform density all the way around, but the different shells could have different densities, so maybe really dense down in the center of the Earth. Now we know the shells aren't really perfectly uniform, but it's not a bad approximation. The differences in the density is pretty small compared to the actual density of the layer. So that's the assumption we make, that it's spherically symmetric. Works great for planets, works great for stars and moons. And then what happens is calculus tells you that as long as you're outside the sphere, the pieces all add up such that the number you want to use is actually the distance from the center. And so that's what this is saying. You use the distance from the center. We assume a spherical, uniform sphere. Calculus says we use that, so that means we can use that in that equation. And oh my gosh, is that a big relief. Because that means that when you're standing on the Earth, every piece of dirt is gravitationally attracting you. You don't have to say, oh, well, how much force due to this piece of dirt? How much from this dirt that's farther away? And all that. You just go, nah, I'm just going to use the distance from the center. So we can do all these calculations, and we get good answers without having to do that. Okay, so now we're confident that we can use that formula. So let's measure, we did the force on the Earth on me. What's the force of the Earth on the Moon? So there's our formula. Now we have Earth's the big mass, Moon's the little mass. There's the mass of the Earth. There's the mass of the Moon. The Earth-Moon distance, that's the average Earth-Moon distance that I looked up on Google somewhere. And that's this many kilometers, so multiply by 1,000 to convert to meters. Plug that into the equation. There's our g, m over r squared, and you get about 2 times 10 to the 20 newtons. That's a lot of newtons. Okay. Let's try a variation on this. What's the force on the Moon from the Sun? So now we have the mass of the Sun instead of the mass of the Earth. That's that number, 10 to the 30, that's a big number. Now we have the distance from the Sun to the Moon, and we use the average Earth-Sun distance, which is one we know. But if the Moon is going around the Earth as it goes around the Sun, then that's a pretty good number to use for this calculation. So what do? Take this equation, plug in the numbers, get out our calculators, do the arithmetic. We get 4.36 times 10 to the 20 newtons. That's also a lot of newtons. But oh look, that's stronger than the force from the Earth that was 2 times 10 to the 20 newtons. So the Sun is actually attracting attracting the Moon more strongly than the Earth is.
Which is sad.
Right?
That means we'll lose the moon eventually.
I'm sorry, I didn't hear you.
It means we'll lose the moon eventually and I'll be sad.
Oh, you think? Well, a lot of people look at that and go, hey, how come the Moon doesn't fall into the Sun? And it turns out that Earth and Moon going around the Sun, if you could stop them in place, nail the Earth in place for a second so it doesn't fall into the Sun, and then let go of the Moon, it's going to fall into the Sun. It doesn't fall into the Earth. You just saw it. It's actually a very simple physics equation. An interesting thing about this is that the Moon is being pulled more strongly by the Sun than its primary, which is the Earth. That's the only moon in the solar system for which that is true. Every other moon is more strongly attracted to the primary. Now, in our moon's case, the Sun is a lot, the Moon is a lot closer to the Earth, but the Sun is a lot more massive for the Earth, and so more massive beats closer. But in all the other cases, that's unique. In all the other cases, closer beats more massive. So, I personally think that we should say that the Moon is a planet And that the Earth-Moon system is a double planet system going around the sun. All the other guys are moons. They're going around their planets. Our moon, nah, it's going around the sun. But what's actually happening there is the Earth and the moon interfere with each other as they go around. So their paths around the sun are kind of wobbly. But I still say moon orbits the sun. Okay, let's go back to the equation for a second here. You notice I got r squared down in the denominator. If r gets bigger, then the force gets smaller. Just like 1 over 8, 1/8 is smaller than 1 over 4, 1/4. So you go out farther still, the force gets weaker still. But there is no force, there is no distance, no value for r that gives you an F of 0. So sometimes you'll hear, oh, it's out beyond Earth's gravity. No, there is no point that's out beyond Earth's gravity. Gravity goes out to infinity. Getting weaker and weaker and weaker as you go, but it still goes out to infinity. So, to be clear, you're standing on a tower at the height of the International Space Station, which is 409 kilometers above the surface of the Earth, and you see the International Space Station go shooting by, and you're really quick, and you look through the windows as it goes by, you see weightless astronauts inside. So what's going on here? Standing on that tower, I'm just as much in space as those astronauts are, but I'm not weightless, but the astronauts are. And it turns out they are because they're in an orbit, and we'll talk about that more in a little bit. So let me check out what my weight is up at that altitude. There's that same formula again, the force. Plug in the numbers, and now for r, we have the radius of the Earth plus the height of the tower, which is 409 kilometers. This is the altitude which the space station orbits, 409,000 meters. Plug that all into the equation, do the arithmetic, you get 753 newtons. When I was down on the surface of the Earth, I weighed 853 newtons. So I am lighter up on top of that tower, but it's a far cry from being weightless. Kind of as an aside, the reason that it wasn't a huge difference is that the only difference between this and the surface, my weight on the surface of the Earth, is the fact that I've got this number here added to this number here. This is what I had in the original one for me on the surface of the Earth. You add the height of the tower. Well, that's actually a pretty small number compared to that one. And so it doesn't make a huge difference, but it did make me lighter. I was only 12% lighter. Let's try something more extreme. What if my tower went all the way up as high as the moon is? So now my tower height is the Earth-Moon distance, this really big number. I plug that in, there's my radius of the Earth, there's my tower height, now it's the big one. Get out my calculator, do it, 0.24 newtons. That's my weight standing on the tower that's as far out as the moon is. Small, but still not zero. There is no distance where it's zero. There's no way of being beyond Earth's gravity. So I just wanted to kind of get that phrase out of our nomenclature. You can't say beyond Earth's gravity anymore.
And I'm going to say this again. That's why you differentiate between pounds mass and pounds force. The what he calculated there was pounds force up there, but his pounds mass that goes in that equation is the same everywhere.
You're making it, that's a good point about the difference between the force and the mass. However, that's one of the reasons I did this in metric units. I never did anything in pounds, so I don't have to worry. My mass is in kilograms, my force is in newtons, and there's never any confusion. One of the problems we have with the English unit system is we tend to think of pounds as being a mass unit, when actually it's a force unit. And if you use English units, the actual unit for mass is a slug, and I'll bet you nobody but the scientists here have ever heard of a slug or used it in an equation. So that's one of the reasons I'm sticking with metric.
Or the gardeners.
He's getting free fall, is the whole point. So, it's static versus free fall, so it doesn't have to do with mass versus force.
Okay, now I want to take a second and kind of take us back to acceleration that I was talking earlier. Remember this equation from Newton, F equals ma. Well, that's the force and the mass, it gets accelerated by that force, and that's any force. So that could be pushing and pulling with a spring, electrostatic attraction, repulsion, anything at all. But most importantly, gravity. So what do? We say, hey, let's take our gravity formula, which you said equals a force, and set that equal to ma. Nice thing about this, they both have a little m on both sides of them. So they cancel. And so that's our formula for the acceleration of an object due to gravity. Now remember, if you get the acceleration, we can calculate the motion. Nice thing about it, the little m is not in there anymore. That means this applies to any object. So let's take a second to figure out what that gravitational acceleration is at the surface of the Earth. There's our similar formula now. Mass of the Earth, radius of the Earth, plug in the numbers, do the arithmetic, 9.8, blah, blah, blah. Now, I shouldn't be displaying all these digits of precision, but I'm actually going to refer back to this a little bit later, so that's why I wanted to show it. As a rule, just think it's about 9.8 meters per second squared. That's the acceleration you feel standing on the Earth. That means if I step off a platform, off a cliff, I will accelerate downward at 9.8 meters per second squared. Same thing will happen if you step off that, or if I drop a pencil or an elephant steps off. It does not matter what the mass of the object is. And that is another thing that's hugely convenient. Because if we had to just recompute everything every single time we were dealing with a different object, then it would be, well, a pain in the butt. So it could be the same thing. I had the numbers in here somewhere. Yep, there it is. Same answer for a 1 kilogram brick as the 11,000 kilogram Kepler Hubble Space Telescope. Same answer for the 685 kilogram Parker Solar Probe as the 300 septillion kilogram planet Mercury. So it's very nice that we don't have to take that into consideration every time. Okay, now remember, and that kind of takes us back to this experiment that Galileo supposedly did, where he dropped two weights off the Leaning Tower of Pisa, two different masses, and found out, boom, they hit at the same time. From what I hear, they say that probably didn't happen, but it would have worked. David Scott in Apollo 15 did that on the moon with a hammer there and a feather, and with no air friction to slow down the feather, they went down at the same speed and they hit the ground at the same time.
On national TV.
On national TV, that's right. Okay.
We didn't go there. Did we?
It's really freaky to watch because you really expect the feather to fall slowly.
Yeah, you're just so used to it. Yeah, it's bizarre. Okay, now.
It's a falcon feather.
That's different.
I mentioned using this formula as the acceleration is constant. Now, back when we did my weight up on that tower, we saw that I was a little bit lighter, or we saw that G was a little bit different. No, we haven't done G yet. We saw my weight was a little lighter because of that tower distance. But when we did that, we could also say, hey, what's my weight on the top of a 10-story building? I was talking about how the difference wasn't huge from the surface to the tower, to the space station tower, because that distance wasn't large compared to the radius of the Earth. Well, if I'm only on top of a 10-story building, that difference is even less. So figuring a story's about 3 meters, so that's about 30 meters up to the top of that building. Here's my new R value. Let's figure out what my weight is, or what the acceleration is standing on top of that. There's the acceleration. Plug in the numbers. Do the math. Now you get this big long number. That's on top of the building. Here's my number for where it was on the surface. They are the same at about fourth decimal place or so. And I don't even trust those last decimal points. So the point is, the difference is really, really, really tiny. And so, as a rule, you can say, look at the acceleration at surface, the acceleration on the top of that building, the acceleration at an airline. This G means gravitational acceleration down, so that's how far you would fall in a certain amount of time. Okay. Earlier when I was talking about the units for acceleration, meters per second squared, I wanted to go over that because I figured you might not be used to that. You're used to miles an hour, but maybe not meters per second squared. You have probably heard of G as a unit for acceleration. Like the space shuttle astronauts undergo 3 Gs during liftoff. Well, that means their acceleration is 3 times that number. So I just want to kind of point that out to kind of bring it back to something you'd heard about. Okay, now let's go back to this idea of I'm standing on this tower, I'm not weightless. The space station goes by, the astronauts are. So what is weightlessness? It's clearly not just being up in space. I'm up in space, I'm not weightless. So, well, wait a minute. When they train astronauts for being weightless, what do? They put them in those airplanes called the vomit comet, and they take it on this trajectory that makes them float around inside like this. So now they are weightless. And they do that because they know, listen, if you stepped out at altitude of the plane, you'd start accelerating downward at 9.8 meters per second squared. Now, air friction is going to get in the way of that. So how about we take an airplane and we accelerate it, there's our formula there, let's accelerate it downward at that acceleration. So now you're falling inside the plane and the air friction's not getting in the way of the calculation. And so if you were a foot off the floor, you're going down the same rate the airplane is, you stay a foot off the floor. So you're falling. So one of my themes, weightlessness, is falling. If you're on top of that tower and you step off, you will now accelerate downward. We figured that number out. It's 8 point something. And there you are falling. And now you take a ball out of your pocket and it's falling at the same speed you are, because of that, Galileo thing we were just talking about. So that looks to you like it's floating as you're falling, just like the apple is here with Stephen Hawking falling on it. They're both falling together, looks like it's floating, looks like they're weightless. So, theme, weightlessness is falling. Okay, hey look, there's the theme. Let's recap a little bit this so far. We got our equation, F equals ma. We got the gravity equation that Newton gave us as well. We applied that to calculate my weight at different heights. The sun, we calculated that the sun's pull was stronger than Earth's on the moon. And then we showed that because of that equation, there is no force, there's no place that's beyond Earth's gravity. And then by equating these two, we got the acceleration due to gravity, which is about 9.8 meters per second squared near the surface of the Earth. And over a small range of distances, g doesn't change by enough, in which case you can use that little formula, y equals 1/2 gt squared. Okay? So, that's weight and weightlessness. Oh look, weightlessness is falling. It's a theme again. Now we can talk about orbits. Okay. How does this weightlessness thing work for astronauts in the space station? So, when I step off, you step off that platform up at the space station height, and you start falling. There's not enough air friction to slow you down. So you just keep going faster and faster and faster, and you get lower and lower, and then bad things happen.
Wow.
But my point there is that you normally think of falling as motion toward the Earth. So it would seem that I'm saying if the astronauts are weightlessness and weightlessness is falling, I'm saying the astronauts are falling. But if the space station's in a circular orbit around the Earth, it's not getting any closer to the Earth. So how can that be falling? Well, let's do a quick check here. I need to calculate little g up at the height of the space station. Plug in the numbers again. That's height of the space station. Into the equation. There it is. It's about 8.7 meters per second squared. So that's my acceleration there from the space station height. How far would I fall if I fell for 1 second stepping off of that platform? Well, now I can use this little g is constant formula, plug in that. I chose 1 second, makes the arithmetic really easy. So I'm just getting half of that. It's about 4.3 meters. That's how far I fall in that 1 second. Now, let's also assume that you're not just stepping off, but you're also moving sideways. So let's turn off gravity for a minute and figure out where you would go with no gravity. So here you are, there's your circular orbit. With no gravity, you just keep moving sideways like this. What that means is, after that 1 second, you're out here. You're farther from the Earth than you were before. So now we can go back and say, hey, how far would I have to go to be 4.3 meters farther from the Earth? Now, I'm going to actually walk through the steps of deriving an equation here, just so you can kind of get a sense of how something like this might be derived. The important thing will be the end result. So let's make this generic. There's our radius of our orbit. It's not the radius of the Earth, it's the radius of the orbit. And there's our distance sideways that we would go. And there's our height, y, away from how much farther away we got. And then there's the radius again. That's a right triangle. What do? Pythagorean theorem. Remember that. Sum of the squares equals the square of the hypotenuse. So here's our sides, r and x. And our hypotenuse is r plus y. Plug that into the equation. There you go. R squared plus y squared equals the r plus y squared. Excuse me, r plus x squared. Now, a little high school algebra, I expand that out to this. And then I go, oh, look, there's an r squared on both sides. They cancel. I got x squared equals this. I take the square root of both sides. There's my formula. So x is the distance sideways you have to go in order to be a distance y farther away from the Earth. Okay? Our new formula. Let's try it out. Plug in, there's our radius of the Earth. There's our y value that we calculated from the fall. Plug it in there, calculate it out. You have to go 7,665 meters sideways. Now, let's do that in 1 second. What's your speed have to be? 7,665 meters per second. So, with no gravity, at that velocity, in 1 second, you'll be that much farther away. Okay, let's turn gravity back on. What happens? In that 1 second, you fall 4.33 meters. They cancel out. So you're not actually any farther away than you were before because the effects canceled. Your sideways motion that would take you away exactly countered the falling that you would have due to gravity. So you actually didn't get any closer to the Earth when you did that. So your radial velocity, that's your velocity up and down like this, and relative to the Earth, that's 0. So it's not like it was before when your velocity kept getting bigger and bigger and bigger when you just stepped off. Because what do? We've just figured out what happened during 1 second. Now I want to say, what happens during the next second? Well, it's the exact same problem again. Because I haven't moved any closer, any farther away. The r values are still the same, my velocity is the same, everything's the same. So that means I just continue around in this circular path. I'm falling, you're not falling down. I'm just kind of going sideways and falling, sideways and falling, sideways and falling. I'm not getting any closer. And if I don't get any closer, if I'm always at the same distance, oh look, I'm in a circular orbit around the Earth. So, weightlessness is falling, orbiting is falling. That's what you're doing. Now, if that kind of makes you feel a little uncomfortable, because you're just so used to the idea that falling should take you closer to the Earth, let's try this variation. Oh look, there's the theme again. Orbits are falling. Okay, let's put me back up on my platform here. Now, if I'm standing there, my idea of the floor, horizontal, is perpendicular to the tower. It's this way. That's my floor. And now, as I'm standing there, the space station goes shooting by. Well, the space station's too big a deal. Let's say a wrench that they lost in the spacewalk is going by. It's in the same orbit as the space station. And it goes shooting past me like this. It's in that same circular orbit that the space station is at. Let's zoom out, see what happens. Oh, look, it has to cross down and go below my floor. So if I'm standing there and I think I see the floor and the wrench goes by, I will actually see it go down from my point of view. So in that sense, it is falling down as it's in orbit. Got closer to my floor and passed it, but it didn't get any closer to the Earth. So, yeah, orbiting is falling. Let's take a second and go back to that calculation for that speed and convert it over to miles per hour. So I had 7,665 meters per second. Convert that to kilometers per second. I know how there's 0.62 miles per kilometer, 3,600 seconds in an hour. Multiply, multiply, multiply. I get 17,107 miles an hour. I Googled the speed of the space station, and they said 17,150 miles per hour. So that calculation's off by about 2.2%. And I think that this basically has to do with the fact that the space station's orbit actually changes. They actually have to boost it back up every now and then because of atmospheric stuff. So to know an exact figure, the figures will differ from time. So I think that's where that error comes from. So my point there, we just figured out how you calculate how fast the International Space Station is going. And what did we use? We used the mass of the Earth, the altitude of the orbit, and Newton's little equation, and the fact that orbiting is falling. Now, we did that in a four-step process. We found a little g based on the radius of the orbit, and then we found how far you fall based on g, that value of g, and our t of 1 second. Then we say, okay, how far sideways you have to go in that time based on y and r. And finally, we get our velocity with distance and sideways. Again, I'm going to show the derivation of a formula. The end point is the important part. And we'll actually get a formula that's simpler than all of this. But this is the sort of thing a scientist would do, working out a formula for this sort of thing. What I'm going to do is I'm going to take the formula for g, I'm going to plug it into the formula for y, get something a little messier, take the thing for y, plug it into x, get something much messier, take the thing for x, plug it into v, and I get something messy, but it's one equation. V equals blah, 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 blah. Okay, so let's start with our g. There's our equation for y. We take this thing and we plug it in, but I'm not going to set t equal to 1 second now. I'm going to say t is still the letter t. We'll leave it like that. Okay, so that's what you do when you get that. Just a little bit messier. Now we have our equation for x, the sideways motion. We're going to take this y thing and plug it into those two places, and we get that. And now it's getting a little messy, and you begin to sweat a little. But I noticed a couple things I can do to simplify this. Here's a 2 times a 1/2. I'm going to cancel out. Here's an r divided by r squared. That'll just be 1 over r. So now that term there just becomes gm over r. Now I look at this and I go, okay, hey, I got a t squared in both of those terms here. So I want to factor that out. So the first thing I'm going to do is take this mess here and square it. So that's this thing. And you go, oh, well, my t squared became t to the 4th, but I know what t to the 4th is. It's t squared times t squared. Oh, look, they both have t squared. I can factor out the t squared and bring it to the front. Then I can take the t squared and bring it outside the square root sign as just t. Square root of t squared is t. So now that's my formula for x. Okay? Now let's clean up our slide a little here and just say that's our formula for x. We're now ready for v rather. Okay, here's our equation for v. Now t isn't 1 second anymore, so I have to say it's distance over time. Take my big X, plug it in there, it's that. Oh look, t over t, they cancel. So now I have that. So now I have one single equation, I can do it in one step. I can calculate the velocity of that orbit by plugging in all the stuff here. Now I'm going to do something a little more sophisticated than just this algebraic manipulation that I've been doing since the beginning. Remember when we said we did a 1 second fall, and we said the distance you cover in that is so short, we can pretend that g is constant. If I had done 10 seconds, g being constant, well, that's a little questionable. If I had done a 10-minute fall, we're way off. There's no way I could have assumed g was constant. The point is, the smaller t is, the more accurate the formula is. And so, do a technique you learn in beginning calculus, which is you take the limit as t goes to 0. You say, let me just use smaller and smaller t's. That means this whole term gets smaller and smaller. If I let t go all the way to 0, this whole term goes away. And this guy, who doesn't have a t in him, survives. So that's the actual correct, most accurate formula. And it turns out to be a pretty simple one. Square root of gm over r. Okay. We got through all of that. Notice that I do want to remind you that this formula that we got by going through all these steps, it's still based on all that geometry we looked at before and on the idea that orbiting is falling. Okay, so let's do an example with it. Let's go back and revisit the calculation I did earlier. There's our velocity, plug in the numbers, there's our r. Now it's a much simpler equation to calculate the numbers, and we get, that's the exact same answer. Now, if I showed all the digits out here, they're not quite the same. They differ out at about the third or fourth decimal point. And this one would be the more correct one. And the reason is that 1 second that we use for the calculation, that's actually a pretty small t value. So it actually gave you a pretty accurate answer. But it's nice to know that if you let t go all the way to 0, you actually get a simpler formula to use that is more correct. Okay. A caveat here, this is the velocity that keeps that thing perfectly circular. So that velocity has to be perfect to be circular. And in a minute, we're going to be talking about what happens if you're not at exactly that speed. But now, I do want to go back, now that we've talked about how orbits are falling, to that question when I said the sun pulls stronger on the moon than the Earth does. Why doesn't the moon fall into the sun? Because it's in orbit. It's moving sideways fast enough to cancel the fall, so that it just keeps going around. It's the same reason the Earth doesn't fall into the sun. It's moving sideways fast enough. And this is where it kind of comes up that, yeah, okay, that would be nice perfect circles. They're not perfect because they are gravitationally interfering with each other, and they sort of have these kind of wibbly paths that go around the sun. But yeah, the answer to why doesn't the moon fall into the sun is because it's in orbit. It's going sideways fast enough. Okay, now let's do a variation on this calculation here. What if the space station orbited twice as high? So now I'm going to do the calculation up here. Twice the height of the space station. So that's bigger there. That's a different number. There's our simple little formula. We plug those numbers in. We get a velocity of 7,444 meters per second, or 16,000 miles an hour. That's slower than the International Space Station. So we just proved a very important rule. Higher orbit, slower speed. And that, of course, means lower orbit, faster speed. Okay, now, let's check Mars on that. When you Google it, Mars is it's about 50% farther from the sun than the Earth is. So that means its path, circular path around the sun, about 50% longer. So that means if it was going the same speed as the Earth, it would take 548 days to go around. Google it, you get 687 days. Now you know why. Not only is it going farther, but it's in higher orbit, so it goes slower. Higher orbit goes slower. Okay, now what if the International Space Station is moving too slow? Let's go back to our little triangle drawing here. Now, here's our original problem. The black line came out here. That was 4.33 meters above. But now it's not going. It's only going to get to here where the gray line is. But in that 1 second, it's still going to fall 4.33 meters. So now it's fallen down to here. So the trajectory curves inside the circle. Okay? What happens if it's going too fast? Now, the path in that 1 second, it goes all the way out to here. It's more than 4.33 meters out. but it's still going to only fall 4.33 meters, so it only gets down to here. The trajectory is now moving to the outside of the circle. So we got two more rules here. If you're too slow for the circle, your path will fall inside the circle. If you're too fast for the circle, it will rise to the outside. So, too slow, goes lower, goes faster. I'm going to skip that example. John, this is the wrong PowerPoint. This is not my latest version.
Beautiful.
Tech support.
That's I can get by with this. Yeah.
I moved it over, I just don't.
Yeah.
It's wrong.
Um,
Just- it's equal to these.
What do you want?
I'll go with this. I'm taking the time. Because what I'm addressing now is what happens with the Gemini guys. And that really should happen before we even talk about the too fast. Once we know this business of what happens when you're going too slow, then we can talk about Gemini. So I drew this as two guys in space capsules, and then I replaced that with the actual Gemini capsule and the Titan booster. This is the problem they had. If you imagine they're both going this way, and this guy wants to move up closer to him, so he fires his rockets, and now he's going slower. What happens to his path? It drops down lower. And so it's now moving lower, and it goes faster, and it moves away. Let's kind of, there we go. Yeah, okay, so the problem they had was when you slow down, it drops into a low orbit, and you go into a lower orbit, and actually, I moved this whole section into when I talk about Kepler's second law. When we get to Kepler's second law, you will see that when it drops down, it goes faster. And that means that the space capsule moves away. In addition, the lower orbit is a shorter path. And so we get around the sun, the Earth quicker, and so even more it pulls away. So it really confused them. Thrusting toward the booster actually moved them away. Okay, so let's recap this. Orbits are falling. Did I mention that? Circular orbits or sideways motion just counters the falling distance. And there's our velocity for a circular orbit. Now let's find out what this slideshow has. Yeah, we did that in a 4-step process. Mess, forget about it. Let's just remember, that's our velocity of a circular orbit. We learned this lesson, lower orbits go faster, higher orbits go slower. If you're too slow, you fall into the lower orbit. If you're too fast, you rise to the higher orbit. Those orbit rules. Actually, John?
Yep.
Let's go ahead and see if we can find one, because right now, what I have in my program is we're ready for part 4, the last part of this thing. Let's stand up and stretch and just disengage for a second so we can get through this last part. This is a long time to be sitting down. I didn't know I was taking my office. Thinking it was good to stop.
No. So. This is like where the Iowa missile silo was in higher orbit. Okay. The higher orbit goes slower.
Someone dropped their
It's like loaded all the time. understand what's the relationship between dropping the spin or blowing up. But the fuel evaporates and so what's the X-ray range? Why is it
All right, you ready to get back to this?
go where they want
I don't want to keep you here all night.
That's the kind of question. Anyway, blue us.
Class is now in session. All righty. Well, we're back onto the right thing, I think. So let's see. Should be. Okay, we worked our way up from Newton's gravity formula, find out about circular orbits. So we're ready for this last thing, which is on Kepler's laws of planetary motion. First, a little historical background. Hey, John? John?
Yes, sir.
Smell the work though.
Oh, it's because we didn't put this thing like
It went on for 2
You know, technical support these days.
Hey, can't you guys talk? Can't you guys talk back there? So I think we still get started. Yeah. That didn't stop. Hold on.
Okay, so we have the right PowerPoint now, so I'm going to restart at the beginning if you don't mind. Yeah.
I don't want to tell you how many slides there are.
Okay. Right, Kepler's laws of planetary motion. Okay, historical background here. Okay, about the year 150, Ptolemy comes up with this idea. Hey, Earth's the middle of the universe, and everything goes around. That's what you saw when you looked outside in the sky. 1532, Copernicus comes up and says, hey, how about this? If the sun is in the center and the Earth is a planet just like all the others, and they all go around the sun, it's a much simpler model. And it does a better job of predicting things unless you take very careful measurements. If you take very careful measurements, you see that even Copernicus, with circular orbits around the sun, doesn't quite predict the right thing. So you got to take careful measurements, and that's what this guy Tycho Brahe was doing in the late 1500s. He was making the most accurate measurements of planetary positions at that time. And he had a mathematician named Johannes Kepler working for him at the time, and he was analyzing Tycho Brahe's data. And Kepler had this idea, okay, I want to figure out why are the planets spaced the way they are? Because for him, there's only 6 known planets. There's Mercury, Venus, Earth, Mars, Jupiter, Saturn, and he can't see any others. Why that spacing? And he has this pet theory. And it's completely wrong. It has nothing to do with reality. But in trying to prove it, he came up with 3 laws of planetary motion based on Tycho Brahe's measurements that are correct. And so we can say thank you to Tycho Brahe for taking such careful measurements. We can say thank you to Johannes Kepler for treating the data as sacrosanct, not his pet theory. It was, another 80 years or so before Isaac Newton came up with his laws of motion and the gravity equation that we've been using. Newton's stuff can actually be used to prove Kepler's laws, but Kepler didn't have that advantage. So he just had to come up with rules that fit the observations. And so the first rule he came up with is the planetary paths are not circles, they are ellipses. And now, I have to take a little time to remind you exactly what an ellipse is, because some of these details will come up later. So, a circle can be defined as points in a plane that are all the same distance from a single point, we call that the center of the circle. And that same distance is the radius of the circle. That's a definition of a circle. Well, an ellipse is kind of similar. It's also points in a plane. But now instead of being all the same distance from a single point, each point on the ellipse is the same combined distance from 2 points. So here's an ellipse, and there's those 2 points. Every one of these points is the same combined distance from those 2 guys. So for instance, here's a point. I mark those 2 distances in red and green. Add them below, like that. Pick another point. The distances are now different, but the sum is the same. Pick a third point. Again, the sum is the same. This is true for every single point on the ellipse. It's what defines the points that are on the ellipse. It's what defines an ellipse. They all add up the same, those 2 distances.
It's like a circle. Now it looks round.
She sees a
Little
sphere.
object.
Not a circle.
Yeah, like
She
a
sees
sphere.
a sphere.
Oh, I could see where it could kind of
It looks 3D-ish.
you look a little 3D-ish. No, everything's flat in this plane, and so this distance here is bigger than the vertical distance here. The 2 points, each is called a focus of the ellipse. And now instead of having one distance, the radius, we have this combined distance. And that combined distance is called the major axis. And here's why it's called that. Let me back up here. The shape of the ellipse is symmetric about the line going through the 2 focus points here. And so we can call that the axis. And so if I pick a point at the very end, like that. Now here I had to draw it just a little bit off the end so you could see both pieces. There's the green length, there's the red length. Now I'm going to take the green length and I'm going to move it over to the other end. Well, it's that same distance from the focus to the end at the other end. And so what I get is this. And so that combined distance that we've been talking about, when you add the 2 together, is just the width, or you might say the length of this narrow ellipse. And that's called the major axis. The width, by the way, is called the minor axis. But we don't care about that. So you can define an ellipse by specifying what your major axis is going to be and what where the 2 points are, the 2 focus points. If the 2 focus points are kind of far apart, the ellipse gets long and thin. If the 2 focus points are closer and closer together, then what you get is something more round and more kind of more fat. And if they're actually the same point, what you now get is a circle. So a circle is a special case of an ellipse where the 2 focus points happen to be the same point. That's kind of nice because Kepler said the orbits are ellipses, and now we know that also includes circles. So you don't have to keep making distinctions. Ellipses are circles. Okay, circles we tend to talk about the radius of the circle, and that's half the diameter. So people do the same thing with an ellipse. They'll talk about half that major axis, which is the semi-major axis. So the semi-major axis is the thing that's most similar to the radius of a circle. Mathematicians like to call it A for some reason. Don't confuse that with acceleration. Tend not to have them in the same equation, so it's not really a problem, but you will be seeing A having a different meaning here showing up. And so properties of the semi-major axis, it's the average distance from the focus for points going around the ellipse. Sometimes going around the ellipse you're closer to that particular focus, sometimes you're farther. They average out to be the length of the semi-major axis. So it's a really convenient thing to use for defining an ellipse. Why do we care about all these details about an ellipse? Why do we care about focus and stuff like that? The reason is when Kepler did his analysis of the data, he found that the sun was not at the center of the ellipse. So his law is that they are ellipses and that the sun is located at one focus of the ellipse. So that's why you're talking about ellipse, you have to remind yourself where the focus is. That's where the sun is. So a little terminology here. Here's our orbit, there's our little sun. The point closest to the sun, that's called the perihelion. The point farthest from the sun is called the aphelion. And though Kepler did all his research studying the solar system and the planets moving around the sun, this is actually not just true for planets, it's true for anything orbiting anything. So they're all in ellipses, and the big thing is at the focus. So if they're close to orbit, you have to talk about center of gravity and stuff like that. So let's just talk about big thing, little thing. So it's true for the space station going around the Earth. It's true for the lunar reconnaissance orbiter going around the moon. It's true for the Mars reconnaissance orbiter going around Mars. It's true for Juno going around Jupiter. They're going around in ellipses. Now, of course, the caveat. Other masses can perturb that. I already talked about how the Earth and the moon get in each other's way, sort of gravitationally moving them off their path as they go around the sun. If you've got a satellite orbiting the Earth and it's going almost out as far as the moon, well, then the moon is going to interfere with that ellipse. And if you've got something going around Jupiter, got those big fat Galilean satellites out there, they'll probably have an effect as well. Simple case, ideal case, we can talk about these things being ellipses. But just know that in reality, when you get down to the details, there are perturbations you can have. If it's going around the Earth, the terms are perigee and apogee. That's that geo for Earth. You might also hear apogee in terms of a rocket flight that doesn't go into orbit. You could launch a model rocket with an apogee of 1,000 feet. That, of course, measured from the surface, not the center. If it's going around the moon, it's perilune and epilune. Going around Jupiter, it's perijove and apojove. And if you're going, the generic case for other planets and moons and stars is the periapsis and apoapsis. So all you need to remember is peri is close and apo is far. Okay, second law. Now remember, we're talking about circular orbits. The smaller orbits, closer in ones, they went faster than the outer ones. So you got to expect, if you're in an ellipse where your distance is changing, probably going faster when you're in close than when you are farther out, just like the circular orbits. So here's an elliptical orbit around the sun, and those dots are at equal space intervals, time-wise, in the orbit. So you can see here, they're far apart because it's moving fast. Here it's moving slow. The time dots are closer and closer together. It's at its slowest out here at aphelion. As it moves down in, it's going faster and faster. And then when it gets down to perihelion, it's going its very fastest. And then as it rises up away from it, it's now going slower and slower. And so Kepler found a very odd way to quantify this. Basically, he found out numerically that if the line connecting the planet and the sun sweeps out an area over time, and his law is equal areas at equal time. So these two areas are actually the same. And you can see that when you're in close, that line has to go farther to get enough area to match this guy when the line is long. So, okay, that's an odd way to quantify it. We're not going to bother quantifying it. We're just going to come away with a lesson. Yeah, you go faster when you're in close. And so, there it is. That's second law. Planets go faster when they're in close. Okay, so now with just these two laws, and there's a third one yet to come, we can say some interesting things about orbits. So let's say I got a satellite going around the Earth. That's that purple plane. I know where it is. I know how fast it's going. I know its velocity, including direction. That's enough to specify the ellipse that it's in. So that's its elliptical orbit. Just knowing the position, not enough. If I know the position and the velocity, that specifies a particular ellipse. So now let's say I'm out here and I hit my thrusters very briefly, just to change the direction of my velocity vector. So now I'm heading this way. So I fired my thrusters kind of this way. What do we know? I'm now coasting. I'm in an elliptical orbit. It's a different elliptical orbit because of that little change in that berm. So maybe it rises above, maybe it sinks below. It definitely passes through this point where you fired your thrusters. So it comes back to that. But now you are in a different elliptical orbit. Okay. And this, in sort of the newer version of the talk, is where I then address the Gemini problem. I already talked about it, so I'll step through it quickly. Oh, no, this is what I talked about next. I'm sorry, got off in my notes. Let's go back to that. Now we're in a circular orbit. Now we're going to fire our thrusters opposite of the direction we're going. So we're just going to slow down. So you see, the blue arrow, that's shorter than the white arrow. So we've just slowed down. What do we know? We're now in a new ellipse. What do we know? One point is right up there. What else do we know? I'm going too slow to stay in the circular orbit. I will descend down. So the new orbit comes down this way. And if you recall, second law, it must be going its slowest here. It speeds up as it comes down here. Going fastest and then slows down again. But up here, what's it doing? It's speeding up as it comes down. And this is where I talk about the problem the Gemini guys had. So there's the Gemini guy, there's his tight booster, there he thrusts. Oh, let's see the cartoon motion lines, they got shorter. That's because he slowed down. That means it's this situation again where your velocity's too low, so your path drops down. But now we know from the second law you're going faster, and so, oh look, the cartoon motion lines are longer, and it's moving away. So the lessons from that, slowing you down drops to a lower orbit. Lower orbit goes faster, so slowing down speeds you up. That's what confuses the guys. And then we talked about the shorter path as well. We go back to the original circular orbit. Now what I'm going to do is hit the gas, aim in the direction I'm going, speed up, the arrow got a little longer. What do we know? If you're in a circular orbit, you're going too fast.
You're gonna start going slow.
You're right, it's going to go slow, but it's going to rise up outside of the circle. So that's what's happening with the path. And then, as you said, as it's doing that, it's going slower as it gets up here, and as it's going faster as it comes back this way. So that's its new path in that higher elliptical orbit. These two maneuvers, except decelerating to drop lower, accelerating to go up higher, that's the basic of orbital transfer. That's how you go from one orbit up to a higher orbit. Now, I'm talking about the simple case where you're firing your thrusters either in the direction you're going or opposed to the direction you're going, so that you're always tangent like this. If you do like I did in the first example, you fire off at the side, well, you get in a different elliptical orbit, and the math is much harder to figure out. But also, this sort of deal is much more efficient. If what you want to do is get up higher, fire tangent to that path, and that's the way to get up there. Okay, so now let's say we're in this low circular orbit here. And we accelerate, we hit the gas. We're now in a higher elliptical orbit. But now what we want to do is when we get out here, we want to switch from that elliptical orbit to the big circular orbit. What do we need to do? We need to speed up, we need to slow down, what's it going to be? Well, we know that if we do nothing, we'll continue back down on that ellipse this way. So what does that mean? Our speed here must be too slow for the circle because it drops down on the inside. So we accelerated here, we get up to here, we're going too slow, we have to accelerate again. So you have to speed up twice. Once to get up into this higher elliptical orbit, and then again to stay out at that higher circular orbit. Let's see what we got here. Right, that's it. You're going too slow for the circular orbit, so you have to accelerate, speed up again to stay in the circle. This ellipse that takes you exactly from this tangent to this tangent is called the Hohmann transfer ellipse. It's the way that takes the least amount of energy to get from this orbit up to this orbit. That's the most efficient way to do it. It has kind of a surprising result. Let's take a look at like a Mars trip. So here's Earth's orbit, here's Mars' orbit. We fire from Earth, we get up to Mars, we get into Mars' orbit. Well, look where Mars is relative to where Earth is. It's all the way over on the other side of the sun. So when you're trying to send something from Earth to Mars, you don't go, ooh, let's do it when Mars is close. You actually want to do it when Mars is going to be as far away as it could possibly be in those circular orbits, all the way at the other end when you get there. And of course, you got to make sure you time it right, so that when you do get there, that's where Mars is in its orbit, which means you have to wait for the alignment to happen right. Now, if you're sending space probes, they probably don't care how long they drift in space. So doing this is the thing to do, because you're sending a space probe, you want to send as much mass as possible. You got a rocket that will lift a certain amount of stuff. You need to get it to this speed. If you could get it to go faster, you just go, hey, you know what? I'd rather just send more instruments. Let me send more mass. So this is the most efficient way to send something. By the way, if you want to come back, here I am going from Mars to Earth. It's the exact same transfer ellipse, except now I'm going the downhill side. So I slow myself down from Mars's orbit, and I drop down like this, and I'm going fast when I get to Earth. So I slow myself down to match it to Earth's orbit. Okay. This has all been kind of qualitative stuff. Can we make it quantitative, where we can do calculations? Because that's kind of what this is about. Kepler's third law is a way to quantify this stuff. What it says is the period of the orbit, that's the planet's year, how long it takes to go around the sun, is proportional to the semi-major axis cubed. Now that's why I talked about all these details about semi-major axis of the orbit. So it's proportional. What's the constant of proportionality? Well, if we use an Earth year as the time it goes around, and an astronomical unit, which is the Earth's average distance from the sun, the Earth's semi-major axis, then it's just going to be 1. 1 squared equals 1 cubed. So you can just set them equal, as long as you're measuring Earth years and you're measuring in astronomical units. So, now what are we going to be interested in? We're going to be interested in finding t, so we're just going to take the square root of a cubed. So that's our last equation for the night. T equals a cubed. Let's go check Mars. You Google Mars, that's its semi-major axis, 1.524 astronomical units. Plug that in the equation, cube it, take the square root, 1.88 Earth years. Convert that to days, 687 days. That's what I said a while ago when I said, hey, Mark, what is the length of Mars's year? We Googled it. Well, now we don't have to Google it. We calculated it. It's 687 days. Okay, so now I titled this talk, Getting Around in Space. So let's kind of do a real example of getting around in space. And I'm going to go from Earth to Mars, and we're going to quantify some of this. So the hard part, of course, is launching off the surface of the Earth in a rocket and getting in orbit around the Earth. Now I'm going to talk about the easy part, getting from Earth's orbit out to Mars's orbit. And we're using rockets, no ion drives or solar cells, and I emphasize that simply because chemical rockets, the way we do it these days, you hit the gas, you fire for a brief time, and then you coast. If you're using ion drives or solar cells, you have this thrust happening the whole way, and that makes the calculations more complicated. So we're just using rockets, we're coasting. When you're coasting, you're in orbit around the sun. So we can use Kepler's laws of planetary motion. So, Earth to Mars, there's our transfer ellipse. We want to figure out the actual properties of this transfer ellipse now. Well, we know that its perihelion goes out to Earth's orbit. So that's 1 astronomical unit. We know that its aphelion goes out to Mars. So that's 1.524 AU. That's the thing we just Googled. So that means its total major axis is just the sum of those two, 2.524 astronomical units. Well, what do we want for our equation? We want the semi-major axis. So you divide that by 2, and we see that the Hohmann transfer ellipse has a semi-major axis of 1.262 astronomical units. We can plug that in here. Do the arithmetic, we come to 1.4 Earth years. That's a full lap, the full period of the Hohmann transfer ellipse. We only want to go halfway. Divide that by 2.7 Earth years, that's about 8.5 months. So that's how long it takes to get from Earth to Mars. And this now addresses the question that I first heard in here a year or so ago, doesn't it take 3 years to get to Mars? No, it takes 8.5 months. Here's how you calculate that. I think what probably happened is that that person heard that a round trip to Mars takes about 3 years. Well, it's 8.5 months to get there. It's 8.5 months to get back. And then something like 20 months to wait for the planets to line up again. So that when you take that Hohmann transfer ellipse from Mars, from Mars back to Earth, Earth will be there when you get there. Because you don't want to just take the Hohmann transfer ellipse and say, hey, we're in Earth's orbit. Where's Earth? Oh, way over there. So that's why I think he thought it takes 3 years, because it's more like a round trip kind of thing. Okay, if you bother to check these numbers for going to Pluto, semi-major axis, about 40 astronomical units. The orbit would be 253 years, so the trip time is 126 years. So, do we think that the New Horizons took the Hohmann transfer ellipse to Pluto?
If we could have 3 generations on the
Yeah, that's right.
a
Yeah.
batch of humans,
All the scientists say they'd be dead.
2nd generation.
So that's one reason when you don't take the most economical path. So, to kind of wrap the last things here, I need to say something about hyperbolic orbits and parabolic orbits real quickly. If you're in orbit around the Earth and you accelerate really a lot, you can actually exceed escape velocity, in which case you ain't coming back. You are not in an elliptical orbit around the Earth anymore. You are heading out. And that's the case. Your trajectory doesn't return. It's not an ellipse anymore. It's now technically a hyperbola that takes you out there. Sometimes you'll hear somebody talk about a parabolic orbit, and that's it's more of a mathematical idealization. If your velocity is exactly equal to the escape velocity, then your trajectory doesn't recur. Now it's not an ellipse, but it's a parabola. So the parabola is the case exactly between being a hyperbola and being a really big ellipse. So mostly a mathematical ideal. But I can't mention parabolas without talking about parabolic trajectories that you tend to hear about. People will talk about the vomit comet needs to fly a parabolic trajectory so that you will be weightless inside. Or fly balls, they follow a parabolic trajectory. Well, if you do the calculations using the constant g approximation, then that's what you get. The mathematical solution to that is a parabola. But you know that's not actually correct. Because you know that g is not actually constant, it actually varies with height. And you know from Kepler that the path of something moving through the gravitational influence of another body is actually an ellipse. So you know that the fly ball is flying in an ellipse. The guy in the pilot, the vomit comet, is actually doing an elliptical trajectory, not a parabolic one, though I suspect he can't actually tell the difference. The point is, anything that's kind of doing that is actually in an elliptical orbit around the thing. So if you want to see something in orbit around the Earth, here you go. Until I dropped it, that was an elliptical orbit around the Earth. Kind of perturbed by the air friction. All right, now I do want to recap the very last stuff so that you can maybe have a better chance of remembering it again. Kepler's laws. Rule 1, there are ellipses, the sun is out of focus. And I reminded you that ellipses have this semi-major axis section. Rule 2, planets go faster in the lower part of the ellipse. Technically, sweep out areas in equal times, but who can work with that? And then we use that to understand what happened with Gemini. Thrusting toward the booster slowed them down. Slowing down dropped them into a lower ellipse. Moving into the lower ellipse made them gain speed. Increasing speed moved them away. So slowing down sped them up. And that's why they were confused. Then there's law 3, which is this. You just have to remember, T is in Earth years and A is in astronomical units. And then we talked about this minimum energy Hohmann transfer ellipse. It's tangent to the inner circle, tangent to the outer circle. Major axis is the sum of the semi-major axis of the two circles. And then you divide that by 2, plug that into this equation to get T, and then divide T in half to actually get the trip time. Thank you for being patient for a very long time. I'll take questions if anybody still has the endurance.
So, go ahead.
I just want to say that, I mean, they put Gemini 4 in orbit. Rocket scientists exist in. They knew what they were doing. What's remarkable to me about your story is that on the scale of a mile or so, that this still mattered. That trying to go towards something meant that you dropped in low orbit and went faster. That people had not recognized that. It's a remarkable story that ties the whole talk together. So thanks for bringing that up.
Yeah, I find it amazing too, and it also has me very curious when you're actually doing docking. Is there a point where you're getting in pretty close and you go, okay, forget the orbital mechanics now, let me fly this like an airplane and just move.
So what is that
closer
number?
when I
That's
get.
what I want to know.
Yeah, I don't know. Yeah.
I always thought that they went out of plane when they're docking, so that they're not like in line with the orbit, but they're perpendicular to the orbit. So
Oh, that brings you in better.
yeah, you don't have those
that would
changes. If you're just going away and closer, they're going in and out. They're coming from a slightly different plane of orbit.
We're doing a transfer orbit to match up.
Oh, they're already, to get close, they do a transfer orbit,
Yeah.
and when they dock, they're a little bit, one side, perpendicular to the orbit to do that.
So you're 90 degrees away, so this doesn't apply.
Yeah,
Right, so you can use your intuition.
yeah. That's what I've been told. I don't know if
But
they
you're
still
talking
do
about
that.
being in an orbital plane that's above the other one?
No, being in the same orbital plane, and
Okay.
the separation is sideways to the orbital plane.
Yeah,
It's the
perpendicular to
vector
your
of the,
But-
of the force, the vector of the force that's changing the velocity. The vector is not tangent, it's it's radial.
I need a blackboard. Then we'll have to really visualize what you're saying there. Because my concern is if you say they're in the same orbital plane, but one's above the other, then they're not in the same orbital plane.
No, they're sideways from each other.
Sideways.
Okay, then one's farther out than the other.
Well, in latitude, one would be at the equator and one would
Same
be at half a
major
degree.
axis, different inclination. So
Okay,
it's
so that's a
exactly
di-
the same orbital period, but they're different inclinations.
Okay, so that's a different orbital plane.
So, but it's the same period, so you can just
Right.
drive straight down to the target.
Yeah, for docking.
Right.
Not for, approaching.
Yeah, I don't know. I have not heard about that, but like I said at the very beginning, I am not an expert in orbital mechanics, so maybe that's how they did it. Yeah, Susie.
You know, like movies like Hidden Figures before computers were doing the calculations?
Yeah?
So humans were actually doing these calculations in reams of paper, and
Yeah.
I cannot imagine how they could keep the accuracy.
Well,
He just did
the
it
impression
right
I got,
I know, but for each calculation that an orbit with humans, go in.
yeah. I'm glad you mentioned hidden.
Yeah.
Yeah.
Can you imagine?
I'm glad you mentioned hidden figures because there's actually, I didn't really have time to go and it will only be relevant to part of the audience here. I'll show the slide anyway. They mention in hidden figures, they're trying to figure out how to go from the elliptical orbit of John Glenn's Mercury flight into a parabolic trajectory down. So they're going to go from one approximation to another, and they can't come up with an analytic solution, how to match those two equations. And they're all standing there looking, and then our hero, what's her name, Katherine Johnson, says, Euler's method. And Euler's method is a numerical calculation now that they had computers. And so these are the basic steps you do in that. You calculate the force, you calculate the acceleration, and then you update the velocity over a tiny time increment. And then you use the velocity to increment to update your position. And then you just loop through that again, and you do that over and over. So what they're doing is just stepping through little pieces of time at a time. And there are improvements on that method that you can do. That's the simplest one to understand. But it's good enough that it's actually what I used in this presentation for all those elliptical orbits that I drew. And computing, what happens if you change your velocity and the dots on the time and stuff like that. So, yeah, that was sort of the breakthrough moment. They transitioned from people doing it by hand to, hey, let's do it by computer.
On your last slide, you mentioned that for planetary motion, the sun is one of the foci. But
Yeah.
for satellite motion, the Earth is one of the foci.
Yes. Yeah, that's kind of what I meant when I said it's not all planets. It also applies to the other guys. They are in ellipses. But yeah, you're right, and I think I left that fact out. That satellites in orbit around the Earth are in ellipses, and the Earth is in a focus. If you send something around the moon is in a focus. So, yeah, John.
Bizarre question for you. Throw you off.
No, good.
How do you calculate the deflection of the photon going around the sun as seen from the Earth, or as it passes near the sun?
That was good.
Oh, you want me to do a general relativity talk? I will do a general relativity talk if there's enough interest.
You're going down.
General
So,
relativity is
there's a-
significant in orbits.
I think for sending satellites up and doing a lot of that maneuver stuff, it doesn't really come into play. But where it does come into play is the GPS satellite system. Their timing is so precise for the timing of the signal going from satellite to the receiver and that sort of stuff, that they have to take into consideration of the general relativity effect of time dilation, which is time slows down for us down here versus up there. So yeah, it really does come into play. I don't know how much it comes into play for orbital trajectories, if they're that accurate. But yeah, for timing in GPS, it does play an important role. Anything else? You all eager to go home?
Thank you.
Wait, did you want it? Did you have that?
Yeah, I gave out the handout.
You did
Yeah.
have it, okay. Now, was it?
All right.